on high resolution spectroscopy. Then we're going to have Jacob Close from York University, and finally we have Antoine Darvaux-Bernier here from Montreal. So I would just say we get started. So we have of the order of 15 minutes for each of you. And yeah, let's get started with Miranda. And she's going to talk about the search for TIO and optical night side emission from the atmosphere of the super hot planet WASP 33b. So I'm excited to hear more about that.
Cool, thanks Bjorn. I will try to share my screen here. There, can everyone see that?
Yes.
Awesome. All right, yeah, so my name is Miranda Herman. I am a grad student at the University of Toronto working with Ray J, who's now at Cornell, as well as Yan Shin here at U of T. And today I'll tell you about the work I've been doing for the last few months, looking for titanium oxide, water, and optical night side emission from the atmosphere of WASP 33b. So why are we interested in titanium oxide in this planet's atmosphere? Well, WASP 33b is one of the hottest planets we know of, and it has a temperature of about 2700 Kelvin. So that means it probably has a lot of similarities to an M-dwarf star, which typically have TIO. And being able to understand the chemical makeup of a planet's atmosphere is really valuable because compounds like titanium oxide can impact the atmospheric structure of a planet. And one example of that is a thermal inversion layer. So a thermal inversion is predicted to occur in the atmospheres of highly irradiated planets with high temperature absorbers like TIO that absorb incident radiation. So this heats up the upper atmosphere, resulting in rising temperature with higher altitude. So instead of having the atmosphere cool pretty much continuously as you move upward, you have this thermal inversion layer where TIO is absorbing that incident light and heating the atmosphere in that region. But how do we detect that? So we can use high resolution spectroscopy to analyze the planet's spectrum. And the high resolution aspect allows us to distinguish individual spectral lines from compounds like titanium oxide and water, both of which have thousands of lines in the visible range. So this is an example of such a planetary spectrum. So this top light gray version shows what we'd expect to see if there is a thermal inversion. So the spectral lines show up in emission, and in the bottom in dark gray is what we'd see if there's no thermal inversion. So we have absorption lines instead. So there are a few ways we can approach this type of spectroscopy. The first is to perform our observations during the planet's transit. So that's when we're viewing the night side and we observe a transmission spectrum. So what this means is we're observing the light from the host star being transmitted through the planet's atmosphere at the terminator region, and the resulting spectrum is going to retain signatures of the atomic and molecular species within, and then we can analyze that. Alternatively, we can perform our observation during the phase curve portion of the planet's orbit. So that's when we have the best view of the day side. And in that case, we're observing the planet's emission spectrum, or the light emitted by the planet itself. One of the challenges with this sort of spectroscopy, however, is that we can't observe the planet's spectrum exclusively from the ground. So any observation we make is going to have contributions from the host star, the planet, and Earth's atmosphere. So we need to be able to remove those stellar and telluric contributions so that we're left with just the contribution from the planet itself. So to do that, we can make use of this Doppler shift that occurs as the planet moves throughout its orbit. So that, of course, shifts the spectral lines of the planet either toward or away from us. And because the planet's going to be moving a lot faster or a lot more than either the star or the sky during the course of our ground-based observations, we can distinguish the planet's shifting spectrum from the mostly stationary stellar and telluric contributions. So this is what an example spectra looks like. So on the y-axis here, we have orbital phase. So this portion covers the transit of WASP 33b. And on the x-axis, we have wavelength. And so you'll notice that the spectra are split into these little sort of boxes. That just is a spectral order. And the first row here shows the raw data from the telescope. And the horizontal bands that we see here are removed when we take out the time-dependent brightness variations in the second panel. And then in this final panel, we remove the stellar and telluric lines. And so that it kind of just looks like noise, but there is some sort of signal from the planet in there. And that's what we're going to use to detect titanium oxide and maybe water in this planet's atmosphere. So to actually do that, you of course can't just measure the lines directly because you can't see them. So we need a separate method to do that. And so instead, we're going to compare our observed spectrum to a model spectrum like this, which is produced by taking things like the planet's temperature pressure profile and the volume mixing ratio of compounds like TiO and water into account. So to do this comparison quantitatively, we use a method called Doppler cross-correlation. So basically what this means is we shift the model to different red or blue shifts and then calculate how correlated the model and the data are at that particular velocity. And we usually compare like dozens of model spectra to our data to see which volume mixing ratio or temperature pressure profile best correlates with our data. So this method allows us to determine things like the systemic velocity, the planet's radial velocity semi-amplitude, and the volume mixing ratios of the compounds we're interested in. So to apply this method to our WASP-33b data, we observed the planet on 8 different occasions. So we observed 2 transits, which you can see here. This is like a looking down on the system. So we observed 2 transits.
Generation your current serval is?
Sorry, could you repeat that?
No, I don't.
Okay. Anyway, so yeah, we observed 2 transits. We observed 5 day-side phase curves and 1 night-side phase curve to see if we could detect titanium oxide or water in any of these portions of the planet's orbit. So this is what the results of that cross-correlation method look like this is for the day-side emission that we've combined all 5 nights of data. In the top is the cross-correlation map. So this shows you how strong the correlation is between the data and a single model we're comparing at each orbital phase. So that's that axis and at a range of velocities to which we've shifted the model. So you get this nice streak here and here that shows that there is a correlation between the data and the model. And you'll notice there's a white gap here just because we don't have observations of the planet's secondary eclipse. Yeah. In the second middle panel is the phase shifted map, where we've shifted each row of this cross-correlation map so that the signal lines up nicely. And in the bottom panel is the phase folded map, which basically means we collapse the above map. And in that way, we can figure out the planet's RV semi-amplitude and the systemic velocity. However, this data is totally fake. It's really the results of injecting a model into the real data at a particular velocity that's known, and then cross-correlating that injection with the same model. So we recover the model we injected. The real data for WASP-33d is on the left here for the day-side emission results. And you can see there's really nothing there. On the right is basically we've collapsed these plots into one dimension. So you can see the strength of this injected signal we recover in blue, and then in black is the signal from the data itself. And the dark gray and light gray are the 1 sigma and 3 sigma levels. So this is for the emission data. This is the same plot, but for our transmission data, so taken during transit. And again, we see no signal from just the data alone, which is kind of disappointing. But this is also kind of weird because titanium oxide has previously been discovered in the atmosphere of this planet. In this case by this Negroho et al. 2017, they also used high resolution spectroscopy to observe the day-side emission from the planet with Subaru. And in this case, they used HST's Wide Field Camera 3, which is low resolution spectroscopy, and suggested that TiO would be necessary to explain the signal they saw. So our results do not corroborate these results. So we can see no detection of TiO or thermal inversion with a lot more data, and in our case, high resolution spectroscopy. But despite this, we can still provide an upper limit on the amount of TiO and water in the atmosphere based on the strength of our recovered injections. So these are those same phase-folded plots I showed earlier, where the colored line is the injected signal that we recover and black is the data. So this is for transmission, of course. And you'll notice that each frame has a different volume mixing ratio. So this would be like 10 to the minus 1, 10 to the minus 2. For water, we can't really say much about the volume mixing ratio from this transmission data, just because even at the highest volume mixing ratio, we can't get a 3 sigma detection even with our injections. But for titanium oxide, if we check out the injections, by the time we get down to 10 to the minus 10, that would be our upper limit on the volume mixing ratio of TiO in this planet's atmosphere. Because if it were any higher in the atmosphere, we would be able to detect it, because you can see at minus 9, there's a nice signal. So we can place a constraint on the VMR of TiO through this data. With our dayside emission data, we can do the same thing, and you can see there's a really nice detection of the injected signal for TiO. And in this case, we can also place a constraint on water of about 10 to the minus 3-ish, because if it was any higher than that, we would again be able to detect it in our data. And finally, we also look at the night side emission data, and probably unsurprisingly, we can't detect anything from the night side. And that's just because by the time we get to this part of the planet's orbit, past an orbital phase of about 0.8, there's not a whole lot of light coming from the planet for us to detect. So it's kind of unsurprising that we don't really see any emission from the planet at this point. But the fact that we can detect no titanium oxide or water at all in the data is, to be honest, a bit disappointing, but we can at least place upper limits. So I think I'm pretty close to my time, so perhaps I will just go over my results. So basically, despite the fact that previous papers have suggested there is TiO in the atmosphere, we cannot corroborate that. And instead, we just place upper limits of 10 to the minus 3 for water and 10 to the minus 10 for the VMR of TiO in WASP-33b's atmosphere. So if you have any questions, I will gladly take them. Thank you.
Yeah, thank you. Very nice talk. Are there any questions? If not, I have one.
I have a question from Miguel. Hey, this is Nick Cowan. Thanks, Miranda. That was a great talk. So are the upper limits that you place, are they strong enough to definitively say that titanium oxide is not responsible for the temperature inversion in this atmosphere? Like I said, I don't know how much TiO you need in the atmosphere to get the temperature inversion.
That is a good question. And to be honest, I'm not sure if, I feel like the fact that we don't detect TiO, but previous groups have, just makes me really reluctant to place any sort of like definitive, make any sort of definitive conclusion about whether or not there is TiO. Because like we have 8 nights of observations of this planet and don't see anything. And we've also, I didn't mention this in the talk, but we did talk with the authors of this paper and compared their models with our data and our models with their data, and just to make sure there's no problem with like the models or the data reduction process, and like they all seem fine. So to be honest, I have no idea what's happening.
So this is Brett Glaman at UBC.
Hi.
I came in a couple of minutes late. I don't understand, based on that previous modeling, do they provide an estimate of the TiO abundance needed to get this? And how does that compare to your upper limit?
So the way they worded it in this paper was a little weird. They basically couldn't say whether the TiO volume mixing ratio was 10 to the minus 8, 9, or 10, because they were all within about 1 sigma. So they decided not to actually place an upper limit and just say that they detected it. So you can see in this plot, I think this was the 10 to the minus 8 model, that there's like a 4.8 sigma detection. So the 10 to the minus 9 and 10 were also roughly within 1 sigma. So yeah, they couldn't place a constraint on it, but did say they detected TIO. So I think, yeah.
Well, I would say, I mean, do they say 4.8? Because it's anywhere between 3.8 and 4.8, right?
Yeah.
The color plot. But so this was
another question here at Miguel. Let me turn around so you can see your questioner.
This is Bill Bedard at Miguel. Have any molecular or atomic species been detected in the host star's atmosphere? What's the velocity of the host star? What would you expect for?
I have a little bit of trouble hearing you. Maybe I'll put my other headphone in.
I think Bill was asking about the stellar metallicity. Like, how much TIO do you expect, assuming the planetary atmosphere is the same composition as its host star?
Right. The host star is a type A star, so it's not like an M dwarf or anything where this might be more common. So I don't think there would be very much TIO in the atmosphere to start with. But to be honest, the star is pretty weird. It's a pulsating star, and it maybe there's something there that we've missed. But yeah, I don't think that the star's composition would be too problematic.
So if you're injecting, so first of all, when you inject the signal into your data, what kind of, do you use actually the same model that they seem to have found in the 2017 paper? Or what is the overall flux level that you put in, or the contrast level that you put in?
I don't actually have that plot with me, but basically we do use like the original model used in that Negroho paper to look at our data, and we couldn't really detect anything with their model, but they used our model on their data and could detect something. So I'm wondering if there's some sort of difference between our actual data, but
well, does it maybe tell us that in some way you are not sensitive to their model, right? So
yeah.
if you, I mean, it could be something that maybe in the data analysis or whatever, that your sensitivity, or from your data with that instrument, you don't get to the sensitivity to detect a signal that they detected.
It could very well be that. I'm pretty confident that there's no problem with like the data reduction process we use, just because like when I inject a model and then recover it, the injection occurs before we do any sort of other like blaze correction or removing the stellar and telluric lines. So that clearly doesn't cause any problems for our injection. But yeah, it could be that our data just isn't quite at the resolution necessary, which I kind of find hard to believe, but
well, I mean, if it's, what it suggests to me is that that you are injecting somehow a stronger planetary signal, and then you're recovering that planetary signal. Whereas if you inject a signal that is of the same strength that they injected, you're not able to recover it. So in some way, I guess what I'm saying is the TIO abundance is not the only quantity that matters, that defines of how strong the TIO signal compared to the star is. But it's more that in some way the overall line contrast that you're injecting, that is what is maybe criteria to evaluate what sensitivity you have.
We did take at least like the brightness of the planet during the emission data into account, and so like scaled our injection by how bright we thought the planet would be at that point in its orbit. But in terms of the contrast, that's a good point as well.
Yeah. Okay. Some nice feedback.
Hold on just a second.
So are you, is there any plan, I guess you're already working with that other team to understand where maybe their signal may be coming from?
Yeah, one of our collaborators is now at the same university as that author, so it's a lot easier to chat with them and try to figure out what's going on. So,
okay. Right, it's an exciting science question, so keep us up to date on this.
I will, thank you.
Thanks for the nice presentation. All right, then let's go to the second speaker. So this is Jakob Kloos from York University. And he will talk about the illumination conditions within permanently shadowed regions at the lunar poles, implications for in situ passive remote sensing.
Okay.
Put it up on the TV screen if you have yours open on there.
Yeah, it is off up here.
On the speakers underneath.
Yeah, the speakers underneath aren't emitting any sounds. It's coming from my laptop.
Okay. Can everyone hear me? It says I'm not allowed to share while someone else is sharing.
Oh yeah, Miranda, would you mind stopping your screen share? Thanks.
The problem is with Jake's laptop.
We had a little reviews where the connects are going on between here and her laptop, so it's kind of reverberating.
Oh, it's gonna quit. Okay, so can everyone hear me still?
Yes.
Assuming that's a yes. Okay, so my name is Jacob Close. I am a PhD candidate at York University, and so I'll be talking about the illumination conditions within PSRs, or permanently shadowed regions of the moon, and talk about the implications for remote sensing. So first, an intro. Minimize this. So permanently shadowed regions are regions on the moon near the poles that are in permanent shadow from direct sunlight. And these are very interesting and very intriguing areas to study, and also very difficult areas to study. They're intriguing because the low surface temperatures permit the existence and stability of volatiles, including water, which is of interest not only for science but also for exploration. And however, these are very difficult areas to study because there are no direct solar photons with which to perform remote sensing observations. And so to study these areas, you have to rely on very faint sources of illumination, or alternatively use your own light source, which may have its own set of downsides from a resource perspective. So in order to study these regions, it's important to understand what illumination sources are available. And it's particularly important for the future exploration of these regions because it can help to guide the design and selection of future instrumentation that we send to these areas. Although these regions don't receive direct sunlight, they're exposed to other sources of illumination, and there are four primary sources. The first is starlight, which is a very faint source, and this is also a broadband source. I won't talk about this too much. The second source is resonant scattering of hydrogen atoms from the interplanetary medium, and this is peaks in the far ultraviolet. And this, together with starlight, is a source. These sources have been used to search for ice at the lunar poles by the LAMP instrument on the Lunar Reconnaissance Orbiter. Third is earthshine, or light reflected from the Earth toward the moon. There was recently some detailed modeling that was done of this particular source as a means for detecting ice within the PSR. So we'll talk about some of the modeling that we did here. And finally, there's scattered sunlight. And of all these sources, this is the most difficult to model. However, it's also the most significant. And I'll sort of talk a little bit about some of the modeling that we've done there. So the questions that were really driving this work are, how do these sources vary in space and time? And sort of how can they be used to detect ice that's in these permanently shadowed regions? So there are multiple reasons why one might be interested in doing this work. These sources of illumination are really the only sources of energy to these very cold regions. And so they sort of control the temperature at the surface and therefore the stability of volatiles. However, our interest in doing this work as of right now is to understand how these illumination sources could be used to detect ice that's present at the surface. And we're specifically looking at ground-based imaging from the surface as opposed to imaging from orbit. which is a little bit more difficult to do. So we're imagining a camera that's mounted on a future lunar rover and exploring these regions. And the way that you go searching for ice on the moon is to take advantage of the absorption bands of water ice. And there's a very strong absorption band at Lyman alpha wavelengths, and there are smaller absorption bands in the infrared at 1.5 and 2 microns. And so by capturing an image in one of these absorption bands and then capturing an image in the visible where there is no absorption, in theory you should be able to compare these two images, and you should really be able to distinguish the ice from the regolith. So in the modeling that I'll talk about, we broke down the illumination into these 4 different bands because these are the bands that can be used, and in fact have been used to search for ice at the poles. So I want to start by talking about scattered sunlight, because this is one of the most important sources of illumination to the PSRs. And the way that you can model the scattered sunlight that reaches the PSRs is to use topographic data from the LOLA instrument on the Lunar Reconnaissance Orbiter. So the topography data that we use is about 240 meters per pixel resolution. And we combine that topographic data with an illumination model, which has been developed by Bruce Hapke and others over many decades. And we sort of follow this procedure for different permanently shadowed regions of the moon. First, we isolate the PSR within the crater. So we're only interested in understanding the illumination that's received to the cold regions where ice could exist. Next, we perform a line of sight calculation from the PSRs to the surrounding terrain in order to understand which areas are actually contributing to scattered sunlight. And then finally, we apply this model in those 4 imaging bands, the far ultraviolet, visible, and then the 2 infrared wavelengths. And the parameters that are needed from this model are found in literature from several papers, and we use the values that they derive for the highlands material, since the polar regions are typical of highlands terrain. So here is some results from this model. This is the results from Faustini crater, which is one of the largest PSRs at the South Pole, one of the largest PSRs on the moon. So on the right is an animation that shows the light that's received to the permanently shadowed regions of Faustini, and it's cycling over 1 year. And on the left, that same value is plotted as a function of time over the course of 1 year. So you can see that the light that's received varies both diurnally and seasonally. And the seasonal variation is due to the obliquity of the moon, which is very small, only 1.5 degrees. But it's, produces a very large variation over the course of 1 year. So between winter and summer, there's more than an order of magnitude difference. So fairly significant. And that's also been reflected in seasonal temperature variations measured by Diviner, which just came out recently. So some of the PSRs, I don't know if you can see my pointer, but some of the PSRs are doubly shadowed from sunlight. So these are very likely the most interesting areas to study because they're the coldest regions. Also, they will be the most difficult areas to study because in order to sort of see into these regions, you need to rely on illumination that's been scattered twice, so it's very, very faint, or even starlight. So there's certainly challenges that exist in studying these areas. So here's results from another crater, Hayworth, which is also located at the South Pole and is one of the largest, if not the largest, contiguous region of permanent shadow on the moon. So you can see that the seasonal variation is very different for Hayworth than it is for Faustini. During the winter, the light, or the light that's received to this area is minimal. It goes to 0 in some cases. And the variation during the summer is more complex than it is for Faustini. And so the juxtaposition of these 2 craters sort of illustrates how complex the illumination can be. And it also sort of highlights the need for models like this, because if we want to send a rover to one of these craters, it's important to understand when we have the best chance of sort of seeing into these very dark areas in order to optimize the science return. So here's a summary of some of the work that we've done so far. So we've applied this model to different permanently shadowed regions. So on the left is a map that shows the maximum irradiance it's received. And that same value is plotted as a function of latitude on the right. So one thing to point out here is that as you move away from the pole, the amount of light that you get increases. And that's simply due to the fact that you have lower incidence angles as you move away from the pole. So the further away you move from the pole, the more light that's available for imaging. However, there's also a downside that you're also providing more energy into the crater, which increases the surface temperature. And so, the more energy you put into the PSR, the more likely that you're going to sublimate the volatiles away. So somewhere in this range, there's a sweet spot of, a cold enough region and still enough illumination to do some science. So another source of illumination is earthshine, as I said. And there was a paper that came out this year that did some very detailed modeling of earthshine. And on the left is a plot of the spectra from this paper, of the earthshine spectra. And on the right is an animation of the earthshine that's being received to Faustini crater. So we essentially took the data from Glenner 2019 and used it to map the earthshine into the PSRs on the moon. So you can see that in comparison to the scattered sunlight, the magnitude of earthshine is reduced fairly significantly. But we applied this technique to all PSRs at the North and South Pole within 10 degrees of the pole. And we applied this over an 18.6 year timescale because this is the lunar precessional cycle. So the main takeaway from this work, and here's a zoomed in image so you can see, the main takeaway from this work is that earthshine is sort of the second brightest source of illumination to the PSRs, but it's severely limited in coverage. So in the North Pole, only about 40% of PSRs actually receive earthshine, and that number increases to 45% in the South. But because it doesn't uniformly cover the permanently shadowed regions, or at least entire craters, its utility as a source of illumination for mapping ice within these areas is severely limited. And here's a plot that sort of compares all of these different sources for Faustini crater. So you can see that both earthshine and scattered sunlight vary seasonally, although earthshine varies seasonally for a different reason. But our main takeaway from this is that scattered sunlight is the dominant source of light to the PSRs. Earthshine is the second, but it has limited coverage. And starlight is orders of magnitude smaller than either of these sources. But it doesn't vary significantly in time, unlike some of the others. And so it sort of represents the baseline flex into these PSRs. So another thing that we're interested in doing with this work is looking at the sources of light in the far ultraviolet region. So on the Lunar Reconnaissance Orbiter, there's an instrument called the LAMP, which stands for Lyman Alpha Mapping Project. And it basically uses starlight and light from the interplanetary medium to map ice within the PSRs. And they have to filter their data in such a way so as to minimize the amount of scattered flux that they see in their data, because then, without an accurate model of how much scattered sunlight is there, they won't be able to sort of map the concentration of ice that's present. So one thing we're interested in doing is understanding, what is the relative amount of scattered sunlight that you get in comparison to the interplanetary medium and bright UV stars. So we gathered data from the SOURCE instrument, which collects daily spectra from the sun in the far ultraviolet region. And we applied our HAPKey model using parameters that were derived from Liu et al., the single scattering albedo, and B, which is a value used in the phase function. And so what we learned from this is that the sources between scattered sunlight and light from the interplanetary medium are fairly comparable, and scattered sunlight tends to exceed that of interplanetary medium during the summer. And this is especially true for craters in the northern hemisphere because they have even smaller amounts of interplanetary medium due to the fact that there are fewer UV bright stars in the northern ecliptic hemisphere. So it also means that during the summer you have roughly twice the amount of photons available for imaging. So to kind of bring all of this together, what we're interested in doing is, again, using these sources to understand, how light could be detected in these images. And so we basically placed a camera near the surface and applied our model to a second bounce of light from the permanently shadowed region up to the camera. And we make certain assumptions about the imagery that you can bring. One of them is the aperture, the size of the diameter of the camera. So we assume that you can bring a 50 millimeter camera, which is fairly large, but not unrealistic. And what we're interested in doing is estimating the signal to noise ratio of a camera that you can, of a camera that's imaging inside of these very dark regions. And so that's what is shown here. That's broken down into the UV visible and those two IR bands. For the UV, we assume a quantum efficiency of 35%. It's fairly low, but it's difficult to make a very efficient camera at that wavelength regime. And so the signal to noise ratio is plotted as a function of integration time. So another thing we're interested in understanding is how long you would need to expose an area of the surface in order to get a sufficient signal to noise ratio to distinguish ice from regolith. So the noise sources that we consider are photon noise, read noise, and dark noise. And sort of our takeaway from this is that the UV is going to be the most challenging region to image in, and that's not exactly surprising, but it's due to the fact that there are fewer photons and the camera is less efficient at converting photons to electrons. And so for about 1,000-second exposure time, you're getting up to, for icy pixels, it's only up to a signal to noise ratio of 5 or 6. And this is during the winter, but during the summer, that increases by a factor of 5. So it means that seasonal variation does make a fairly significant difference in terms of the signal to noise ratio. For the other bands, it's a little bit less significant because there are more photons available and because you can have a CCD that's a little bit more efficient. So the trade-off of imaging in the infrared is that there could be other minerals that absorb at 1.5 and 2 microns, which may lead to a false detection of ice. And furthermore, there's less of a separation between ice and regolith. And so it's a little bit harder to actually detect the ice that's there. Okay, so that's all I have, and these are the conclusions. So, just to reiterate, we analyzed all of these different illumination sources within permanently shadowed regions, and we find that scattered sunlight is the most significant source, but it does vary significantly in time. And at UV wavelengths, it's also true that scattered sunlight is the dominant source, although light from the interplanetary medium is sort of comparable at certain times of the year. And Earthshine has limited coverage, which means it's not an ideal source to go searching for ice at the poles. And we've also been conducting some experiments in the lab in order to validate some of this work. And those are just sort of wrapping up right now, but those have sort of led to some fairly encouraging results, which I'm happy to talk more about if you're interested. So I'll leave it there and take some questions.
All right, thank you, Jacob. We have time for one short question.
Can you turn your volume?
My volume? Okay.
Can you say anything about how long the ice would last? Is it billion-year-old ice or 1,000-year-old ice that you think you're looking might be able to see?
Sorry, I missed the beginning of that question. Is it how long has the ice been there?
The question is about how old the ice is. Is the ice thousands of years old or millions of years old?
I think it's on the order of thousands of years. It sort of depends where you're looking, but for the coldest regions, the largest source of loss is micrometeoroid bombardment and sputtering due to solar wind that gets deflected into these areas. And based on those loss rates, ice in the upper 500 nanometers of the surface can only last for a couple thousand years or so.
Does that differ if there's ice deeper in the subsurface?
Yeah, so the ice could last for much longer, deeper in the surface, but obviously we wouldn't be able to see that with a camera.
All right, then I would say we go to the next speaker because we have only 15 minutes left. So our next speaker is Antoine, and he's going to talk about his recent work on Spirou that he has done.
Gonna share the screen.
And while you're doing this, maybe a general comment. I think what we have to make sure is, because I planned so far that we have always 15-minute talks, I would like us to stick to the 1 hour though in total, if we can somehow arrange this. So for the future speakers, I think this today is good, but for the future speakers, I would suggest that we really aim for something for the students between 10 and 15 minutes. So if you have a talk that is 12 minutes, that's perfect, or 11 minutes is perfect. Let's try to not have talks that are 20 minutes, because it would be nice to have actually a discussion. And I think we had a bit more time to discuss for the first talk, and it would be nice to have this, to give this opportunity for every topic that is being discussed. So for the students that are listening, let's keep it between 10, or let's aim for something like 12 minutes or something like this.
Do you see my screen?
Yes.
Okay. Okay, so hi, my name is Antoine Darot-Bernier. I'm a PhD student at the Université de Montréal. I'm under the supervision of René Doyon and David Lafrenière. I'm going to talk about high dispersion emission spectroscopy with Spirou at the CFHT. So Spirou stands for the spectropolarimetre infrarouge, which translates into spectropolarimeter in the infrared. It's installed at the Canada-France-Hawaii telescope on the Mauna Kea. It's a fiber-fed spectrograph from the Cassegrain focus, which is, you can see it in the cartoon. This is at the base of the telescope. And the fiber is here and connects to the spectrograph, which is in another room on the basement of the telescope facility. And you can see also with the cartoon that the instrument is very huge. It's a huge spectrograph. Spirou's main goal is to detect Earth-like planets in the habitable zone of low-mass stars with the velocimetry method. This is what I'm showing here. You want to measure the reflex motion of the star due to the planet and see the Doppler shift in the line to detect the planet. Here it's just an example of the type of star Spirou is made for. So it's the TRAPPIST system. It is a very good target for Spirou because the flux is stronger in the infrared, and it bears a lot of molecular lines. And you can observe molecular lines in the infrared. Though the system doesn't need to transit to be detectable with Spirou. Here, to fulfill this goal, Spirou is reaching for an RV precision about the meter per second. So that's very precise. This means that it has to stay extremely stable. That's why it's embedded in a cryogenic vessel here with the temperature stabilized at the millikelvin. So it has to be really, really stable. It also needs a high resolution. this allows to resolve each individual lines, like it's shown in the figure here. It's a synthetic emission spectrum of a hot Jupiter. And you can see that at Spiro's resolution, which is in blue, the blue line, you can resolve all the individual spectral lines. These are water emission lines. So it's not noise. It looks like noise. Oh. It looks like noise, but it's not. And if you get to lower resolution, you can see that you lose a lot of this information, and especially more specifically in the green line. If you look at the green line, it's nearest resolution at 700. At 700, and you can see that you're losing. And nearest is for those who don't know, it's one of the Canada's contribution to the James Webb Space Telescope. And you can see that you're losing most of this information. You only keep the broadband information or the strongest lines. And so this was a zoom on a tiny, tiny part, 0.9% of the Spiro's bandpass. Now, if you look at the whole thing, it looks like that. So you're not able to see all the detail. And that's what makes Spiro a very unique instrument. It's the combination of the large coverage from 0.95 to 2.52 microns, and it's very high resolution. So with a single exposure, you get all of this. But to get that, you need an insanely crowded detector. It looks like that. So yeah, here it's Hawaii 4RG detector. And the fake colors are here to indicate each order of diffraction. So Miranda talked about this earlier. So you get the 49 order of diffraction from the red to the blue. And if you zoom on one of them, you get that. So you can see that for each order, you have 2 scientific channels and 1 calibration channel. Fortunately, I don't have to play with these images because some courageous people are doing the extraction for the observers. What we receive at the end is a spectrum for each 49 order of diffraction. So each of these lines gives us a 1D spectrum. Now, when you observe in the infrared, one of the biggest challenges is to deal with the Earth atmospheric absorption, also called the telluric lines or tellurics. What I'm showing you here is the telluric spectrum on Spiro bandpass. You can see that there is a lot of absorption from the water in blue. Like at some places in the spectrum is just, you don't get any flux. And if we scan the whole bandpass, you can see that there is some methane absorption, some oxygen O2 absorption, ozone, a lot of big absorption bands, again, ozone and some CO2 lines here. So there is a lot of telluric absorption in the infrared, and this is an inconvenience, but it's also an advantage since it is a very rich range in spectral information, and that's what we're looking for on exoplanets. For example, on a hot Jupiter, you're looking for water, CO, CO2, and maybe not methane, but on colder one, we're looking for methane. So that's also a good thing. Here, yeah, just to illustrate this, this is a spectrum of a synthetic spectrum of a hot Jupiter. And you can see that you have a lot of, again, it's on the Spiro's bandpass, and you can see that there are a lot of absorption band from water. You get the CO absorption, 2 CO absorption bands here, some lines, potassium lines, and sodium lines. So it's very rich in information. Now, how we do it, it's similar to what Miranda explained earlier. We observe this, okay, I will just present this figure before. So you have the wavelength on the x-axis, the orbital phase on the y-axis, and the spectrum is just color-coded in gray. You can see the absorption lines from the star or the telluric lines, and they are not moving through time. But if you're looking at the emission lines from the planet, which are in white, you can see that they are moving on the detector. And that's the effect we're using to detect the planet signal. There are two main moments where it's better to observe: during the transit, as Miranda talked about earlier. And if you are looking for thermal emission, you're better to observe right before, around the eclipse. And I'm going to talk more about the thermal emission in this case. But you can also do the transit, but I'm just not doing this technique. Now the data processing, again, you're used to this kind of figure. It's the same thing as Miranda showed earlier, but this is for a single order of diffraction. So you have the raw 1D spectrum at each moment. These are actual data, pure observations. First, we normalize each spectrum. And now you can see the stellar lines that are not moving through time. They are quasi-static, and maybe some telluric lines also. Some are masked here in white. And to get the planet signal, you have to remove all this quasi-static signal. There are many ways to do that. We use a principal component analysis to get what you can see at the bottom panel. And just to illustrate where the planet signal will, how the planet signal will behave, this is the, if we have had a single line, this is where it will be. So it will move on the detector. And again, we don't see any planet signal in this, and this is normal. Just to illustrate this, this is a model. This is the relative of the relative signal we expect to get on the detector. It's about hertz per thousand, 0.1 hertz per thousand. And if you compare it to a single exposure on the detector, you get that. So yeah, there is no chance to see the model just with an exposure, or to combine it. It will be very difficult. So you don't get this. You cannot observe this directly, the spectrum of the planet. It will need to be 100 times stronger to be able to be at the same level as the noise level. So the technique, we use the cross-correlation technique. This is just an example for this configuration. So right after the eclipse, we get the egress and some movement after the eclipse. That's what it will look like on each exposure. You have the wavelength from the blue to the red. The eclipse is here, so you don't get any signal. The signal appears after the eclipse, and it's getting Doppler shifted in the blue because the planet is going towards the observer. And how do we extract it? We use a template of the planet spectrum to look like that in color, if you want. And we shift it at different radial velocity, and you get a cross-correlation function like that, and a peak at the good radial velocity. So you get some noise, but the strongest peak should be at the radial velocity of the system. Now, with real observations, it looks like that. These are, so it's the same configuration as I showed in the previous slide. It's we observed right after the eclipse. You get the egress here, and the signal is expected to move like that. These are all cross-correlation functions at different time. Yeah, maybe we can see something, but it's not clear. It could be noise as well. And yeah, so what we need to do is to stack all the signal, where we have to try at a different semi-orbital, semi-amplitude. So it will change the angle of the planetary signal. And if you combine it at different KP, you'll get a map like that and co-add it. So here is our signal. It's not, so it's at the expected semi-amplitude, but the signal is a bit shifted compared to what we expect. So to confirm this detection of the atmosphere of a hot Jupiter, we would need we are waiting for other observations occurring this semester. And we will also try to test different models, so atmospheric models of the hot Jupiter. So in conclusion, high dispersion spectroscopy is a good way to characterize exoplanets. SPIRO can detect thermal emission of some hot Jupiters, and you all have access to SPIRO. You can ask, submit a proposal at the next semester. And we are waiting for a second visit to confirm our detection. Thank you.
All right, Antoine, thank you so much. And we have time for a couple of short questions. All right, maybe I have one. So what was the model that you used right now? Like what parameters that you use for the model that you put in there right now?
So it's at the expected temperature of this planet. It's there is no thermal inversion. It's like a basic. It's from Scarlet. It's from
right. It's a fiducial model that is one time solar and
yeah.
Okay.
Yeah, it's so yeah. Next step is to try a lot of different models.
Yeah. Yeah, I mean, I can certainly make you a whole bunch of models, or Stefan or someone, but about this more. This is still from the first. This is all from the first transit, right?
This is not the transit. It's the.
Oh, this is the okay. This is the emission. Yeah, that's right. Okay. Are there any other questions? All right. I mean, we are at 1 o'clock anyway. So in the end, I think it came nicely out to 101. That's great. Yes, then I think we can close the session for today. We will have another meeting in 4 weeks from now, where we, I think, also have 3 grad students speaking again. Let's thank all together the 3 grad students that spoke today for their nice presentations.
And Bjorn, if I could just say something real quick.
Yes, sure.
So just a reminder, so if you're unable to make one of these seminars, please do watch it afterwards. We post these on YouTube. And remember that we have to show 100% compliance and attendance with NSERC. So once you've had a chance to do that, go ahead and email Anna to let her know that you've seen the video. And if you know somebody who couldn't be here today for any reason, just pass along to them as well to take a look on YouTube, watch the seminar, and to let Anna know once they've done that. All right, thanks.